Welcome back, AP Calculus students. Today's targeted review is on volume, and it says area. It's really area between two curves, since like half of calculus is about area, so it's about a specific area. As usual, I'm going to ask you to go through and do these three problems. I have three free responses, one per page. And then if you get stuck, come back and watch the video. At the end, we'll do some conclusions. I'll try to teach you a couple cool tricks with the graphing calculator, because the first problem is calculator active, the other two are not. And then you should be feeling pretty prepared. Usually, I can't say every year, but usually on the Calculus AB exam, there is one of the 6 free responses that focuses on volume. Lately, it has not been on the calculator active section because there are more and more programs that you can put into your calculator that just say, if you want to find the volume of a solid when you do this, just put in the different numbers in the problem. You put them all in and it says, here's the setup, here's the answer. So they're trying to get away from that, and so that's why I picked more calculator non-active problems. But it could still happen on calculator active, and we'll go over one of those as well. All right, first one. Let R and S in the figure below be defined as follows. R is the region, and this one is a little bit tricky. I don't really like where they put R here. But they say R is the region in the first and second quadrant. So here's my first quadrant, and then here's the second. So everything that I'm doing in green, and I'll do that over here, is R. Right? S is much easier to see. It's the shaded region. We also have two graphs. We have y equals 3 minus x squared, negative x squared plus 3. This has got to be my downward facing parabola here. I'm actually going to rename this too. I'm going to call this f of x equals 3 minus x squared, so that instead of writing 3 minus x squared, I can just write f of x. That means you won't make any mistakes with parentheses or anything weird. And then we'll do the other one, which is y equals 2 to the x power. That's our exponential over here. We're going to call this g of x equals 2 to the x. All right, this is calculator active. I always spend the first minute or so just doing things with the calculator. There are a few points that we're going to need on here, and I'm going to find pretty much all of them. We'll need the X-intercept over here. We'll also need all 3 of these intersections, and your calculator is going to be very useful for that. I'm also going to need these 2 in my calculator. I'm going to show you a different way to put them into your calculator right now too, maybe a way you haven't seen before, maybe a way that I have gone over and have just forgotten about. So let's get to it. I'm actually going to, in my calculator, call the red equation f of x and call the purple equation g of x. Almost said green, but no, I'm pretty sure it's purple. Well, how do we do that? Well, instead of going to my graphing screen, I'm actually going to go to the calculate portion, and we're going to use something in menu and then actions. We're going to do menu, actions, and then define. Define is actually super powerful. You need to use function notation. You can use more than one input. We're only going to stick with one independent variable here. And I'm going to define an equation called f of x. And it's good that it doesn't turn bold. If it turned bold, then that would mean something is already in there for it. But we're going to define f of x as, so we need an equals, and then I said I was going to call f of x 3 minus x squared. So it's going to be 3 minus x squared. Then I'm going to hit enter. Now, if I want to use f of x, like for example, let's find something easy. Let's find f of 0. If I wanted to find f of 0, notice f is bolded. F of 0, that's going to be 3 minus 0, which is 3. I will get 3. And this gives us a way, instead of graphing, to just name our equations. And I'm going to do the same thing with g of x. Menu, actions, define. We'll call this g of x. And that's going to be equal to 2 to the x power. Now, it's not always useful to do this, but I like my names to match up to what I named them over here. So I figured f and g, let's call them f and g. Do you need to graph these? Well, I would if we want to find all these different points on here, right? So we're going to go back, and I'm going to graph my first equation. What is f1 of x? Well, I'm not going to do 3 minus x squared. I'm just going to say f1 of x is going to be the function f of x. Right, I've already defined it. That is 3 minus x squared, and we're good to go. What about f2 of x? Oh, that's going to be g of x. Now we can see all of our intersections and points. Let's find those 2 intersections first. So menu, analyze, graph, intersection, that's 4. We get not such a nice number over here, but we are going to do a couple extra pieces. We should also probably define these at some point. I might need this one, so I'm at least going to do the x's. I'll come back and do the y's later. I'll define that as a. If it turns out we have to do right minus left or left minus right, I'll come back for that one. But I'm pretty confident we won't, because right minus left would be the same equation. Top minus bottom makes more sense. We're looking at the x's there. So let's go ahead. The y-intercept is easy, isn't it? Right? I think we should know how to find a y-intercept. You just replace x with 0. So my y-intercept is just 0, 1. That's not bad. This x-intercept was negative 1.636. Negative 1.636, comma, the y was 0.321. There we go. I think we still have to do that upper one. However, when I find that, you're going to say, oh, duh. I mean, it looks like the point 1, 2. Maybe it is, maybe it isn't. But when you analyze graph intersection, it is 1, 2. And visually, that makes sense. If x is 1, y is 2. If x is 1, y is 2. So we get the point 1, 2. Very nice. And then what about this last x-intercept? Well, one way you could do it is you could find the x-intercept. You could find the 0 here. But you should be comfortable finding x-intercepts of parabolas, right? To find an x-intercept, you replace the y with 0. So 0 equals 3 minus x squared. X squared equals 3. Does not imply that x equals plus minus the square root of 3, right? We see these two x-intercepts here. So this is the square root of 3, 0. I'm doing this all ahead of time so that we can really just use our calculator to save time. So that took me, about 2 minutes, give or take? 2 out of 15 minutes allotted for this question. But now we've done all the hard math. We just need to put all this into calculus. So find the area of S. Well, if I'm looking at S over here, I see 2 ways to do this. One way is that we can do my top function in purple minus the bottom function I'll do in blue down here. And if you do purple minus blue, that'll be fine until the first intersection. But then notice we're going to have to switch and do red minus blue to finish it out. That is compared to going the other way, where we could do red minus purple, all the way over until here, and then we would have to do red minus green. And I think the issue with that is then we would have to solve each of those. If we're going right minus left, we'd have to isolate x for each of them. So I think by the time we do that, we might as well just do top minus bottom and write 2 integrals. Okay, so my 2 integrals, and I'll try to illustrate them. First one's going to be in purple up until an x value of 1. We know it's an x of 1 because that's right there. So it'll be the integral. We start at 0. We go to 1. My top function is 2 to the x, which I did call g of x, so it's whatever you'd like to do, 2 to the x, minus the bottom function, which is just along the x-axis. That's y equals 0 dx. And that'll get sum of the area. You might ask, do I have to put the minus 0? No, you certainly don't. I like to put it to remind you that there are always 2 functions. You're doing top minus bottom, but you totally don't have to. Then we have the red one to complete this off, right? My red functions, we need to add on some more area from 1 over to my last x value, square root of 3. My red function I called f of x. And then the bottom function is again 0, right? dx. They did actually want us to find the area here, so we should probably take care of that, right? 0 to 1, 1 to square root of 3. So we're going menu, calculus integral, 0 to 1. And you could type 2 of x, you could type g of x, whatever's faster for you, dx. And then we need to add that on to another integral, this one from 1 to the square root of 3. F of x minus 0 is just f of x. And all of that dx, and we should be set. Nice. My calculator again tried to be very helpful, didn't it? And it said, here's the answer. You could write this as the answer, or we could just do the nice decimal approximation, 2.240. Some people ask, well, wait, do we need to put the 0 at the end there, you actually do. You would lose points if you just wrote 2.24, because what you would be telling the graders is that it is the exact answer 2.24, and it is certainly not. You need the 0 there. When in doubt, just go further than 3 decimal places, and you're fine every time. All right. Find the volume of the solid generated when r is rotated about the horizontal line y equals -1. So we're just dealing with r here. I always like to draw these. You don't have to. It's up to you. So I know that it's going to be equally above as it is below. And then r I'll do in 2 different colors. We'll do the one in red first, which kind of goes up like this. And then I'll do the purple part, which comes over like this. Then I need to reflect that, and it's going to be, I don't know, something like this. Doesn't have to be perfect. And then we have the purple one, which is reflected. I didn't do a great job there, but that's fine. Something like that. And then we have the line y equals -1. So that is what we reflected over. Probably do that in a different color just so it stands out. Okay, and then from here, I always like to fill in those circles. So we've got this guy like so. Okay. And why don't I just focus on this circle first? So if I wanted to find the volume of these, if these disks were solid, they're going to be open, but if they were solid, then the distance, or the radius, is always the distance from the purple function to the line of -1, and we know how to find the area, the distance between two functions. We do the top minus the bottom. In particular, we want to do the two that we know. So someone might say, well, wait, couldn't you do the line to this bottom function? You could, but I don't know the equation of the bottom function, so we're going to try to make it easier on ourselves and just do top minus bottom there. So if I look at that purple guy right here, and we have this radius, right? My radius is the top function, 2 to the x, minus the bottom function, which is -1. All right, let's do the red ones. So the red one is kind of in the same spot here, so that's harder to see, but then we can start to move around like so, right? There we go. And so don't forget that what we're really finding here is the washer like so. Okay, this red circle, we're again going to do top minus bottom. That's, if you wanted to look at the radius, it is this guy right here. I'll use a capital R, that's the larger radius, and my larger radius then is going to be 3 minus x squared minus -1. All right, let's do those integrals. These are circles that are being spun, so we need a full circle. That's pi r squared. So we have the larger one first. We're going from what to what? Oh, right, we found those earlier, didn't we? We're going from -1.636 all the way over to this guy, so all the way over to 1, okay, of pi times big R, which if you do some math, 3 minus x squared plus 1 squared, right? Then we need to subtract off, in purple, the inside piece, right? We want to subtract off all these disks to get it hollow. So minus pi times the little r squared, which is 2 to the x plus 1, ending, of course, in a dx. Notice that you can factor out pi as well. And I think from here, we just turn to our calculator to finish all of this off. So notice on your calculator as well, we called this f of x, and this is g of x. So that might help you shorten things a little bit. Let's get to it. We know that pi is on the outside if you factor it out. So pi times the integral from, and I think I saved that as a, didn't I? Let's see if I was that clever. I did. I saved that as a. That's really nice. So I can just go from a to 1 of big R, and it might help you to look at your paper here, right? Big R, I think in this case, is going to just be f of x plus 1 squared minus, and then we have little r, g of x plus 1 squared dx, and hopefully that is it. 63.1066 looks fine. Just a friendly reminder, let's say that you switched these up. Let's say that you did g of x like so. Notice it's the exact same answer, just negative, and that will happen every time. So that's kind of nice here, where you know, because we're dealing with tangible volumes and areas, that the answer should always be positive. So if you don't get a positive, you're probably right. You probably just switched the order there. And so just try switching the order, see if you get the same answer. If it's positive, you probably did everything right. You would lose points for writing it like this, but it's easy enough. Just cross off the G, cross off the F, change them, and you'd be just fine. So either way, we end up with 63.1066, whatever you wanted to do there. Awesome. Last but not least, region R is the base of a solid. For this solid, each cross-section is perpendicular to the x-axis. Whew, that's good. No y-axis. There's an isosceles right triangle with one leg across the base of the solid, right, but don't evaluate. Okay, a little bit tricky here, so I'm going to take that area of R again, right? And R looked something like this, and then it had this guy kind of curving in. And then we need to get our drawing caps on. I'll do this in green. We have an isosceles triangle, and this is a little tricky if you don't remember what an isosceles right triangle is. So start with a right triangle first, right? A right triangle could look something like this, as long as it has a right angle. But the isosceles part is the part that tells you that this triangle has to have two sides that are the same. And for our right triangle to have two sides that are the same, those have to be the legs. They have to be equal. And they're telling us that one leg is across the base of the solid, perpendicular to the x-axis. So if this is my x, perpendicular means going down this way. So I'm going to go ahead and do my best to draw a triangle. Always one of my trickier shapes to get in here, but I think it looks something like that. Can we see the right angle that's hiding in there? Right, these two legs are equivalent, and then if we wanted to give it that third dimension, looks something like this, right? Can you see it pointing off the page at you? So there's that. It doesn't matter if you drew it the other way as well. You're like, but I like see it kind of standing up this way. That's fine. You'll still get the exact same area. Nothing's going to change here, as you'll see in just a second. But either way, whatever works best for you. I'm going to go ahead and get rid of that second drawing just so I don't confuse us. Okay, well, let's go ahead and look at this guy right here, which is the base of our triangle. Right, the base of our triangle is the distance from the top function minus the bottom, so that is f of x minus g of x. The height is the same as the base. That's the whole point of an isosceles triangle. How do we find the area? Well, area is 1/2 times a base times a height, but with an isosceles, the base and the height are the same, so really it's just 1/2 of the base squared. How do we find volume? Well, volume, we go through and we add a third dimension, right? Volume is going to be 1/2 the base, which was f of x minus g of x, squared, 2 dimensions. The third dimension is this infinitely small slice across the x-axis, which is dx. That, though, will only give us one triangle. We need to sum up every triangle across this. So integral from what to what? Oh, that's that negative 1.637 up to 1 again. And I think we're done, right? But do not evaluate. I think we did everything there. I used f of x and g of x. You, of course, could have written 3 minus 2x minus 2 to the x, and you'd have been fine too. That's that. All right, moving on to our second problem. Functions f and g are given there. It's no calculator this time. I might as well highlight in colors what we're dealing with, though. So here is f of x, our beautiful square root function, and then g of x is that 6 minus x, that linear function with a negative slope. R is the region bounded. Cool. Find the area of R. All right. We're going to do this in 2 different ways. If I'm looking down here, though, no, we'll talk about that in a second. So we'll do 2 different ways first. So the first way I'm going to do is the way that I think you guys are more comfortable with, which is that top minus bottom. Right? So top minus bottom's along the x-axis. The first one I'm going to do is the red area until I get to an x of 4. And then the second one I'll do is the green area from 4 to 6. Okay, so find the area of R. We're going to find the integral from 0 to 4 of f of x dx. And since I'm actually going to do the math, we might as well write this in. X to the 1/2 is the square root of x, right? Plus the integral from 4 to 6 of 6 minus x. dx. Let's work through it. Antiderivative, we add 1 to the power, and then we have to offset that power. And then over here, similar idea, 6x minus 1/2 x squared, 4 to 6. Start substituting in. I'm going to factor out this 2/3 and deal with that later. Don't forget that a 3/2 power really means the square root of the value cubed. 0 is just going to be 0, but I put it anyways just so we can see that fundamental theorem. You do not have to put the 0. Same thing over here. We're going to go through, and I'll use parentheses so that we can see it's 36, 6 times 6, and then half of 36 is 18, right? Minus, and then the second one, 24, 16, half of 16 is 8. Okay, and this is a free response. I would stop right there. If you'd like to simplify, you can, but I don't know why you'd want to. That's just extra math to do, right? So you could go through and get your answer, yay, but yeah, again, I really don't want to do that. And it's going to end up being some weird fraction too. I think it ends up being like 22/3 or something like that. But yeah, just stop here. This is a valid answer. I promised you 2 ways though, and the other way is the way that you've of course seen a few times before, and that is the right minus left method, right? This is the one where we're going to go sideways, where we go this way. Okay, we actually start from the bottom. We go from 0 all the way up to 2. Okay, so we need to integrate from 0 to 2, but because we're going along the y-axis, it's going to be dy at the end. Each of these little, you can call them rectangles, has a width of y, which means every equation in here, when we do our right equation minus, and I should have given myself more room here, minus the left equation, okay, needs to have y in it. Currently they have x, so let's take a quick second. Let's look at this. I'll keep in the colors. Y equals square root of x. We of course square both sides to get this in terms of y. Then g of x isn't bad. 6 minus x. Add x, subtract y, and we're here. So to create that same green graph but written a different way, we can do the function 6 minus y. To create the same red graph, we can do y squared. Notice then that when we do our antiderivative, it becomes 6y minus 1/2 y squared minus 1/3 y cubed from 0 to 2. We know substituting 0 into all those will be 0, so I'm just going to substitute in 2. This becomes 12. 4, half of 4 is 2. 8, half of 8 is, or 1/3 of 8 is 8/3, and that's as far as I want to go. Sounds good to me. Again, if you simplify, you'll get the same 22/3, but I think you might realize that once you've done, or once you've converted these equations, this way is actually a little quicker. Now you might say, well, I don't like that. I don't want to do it. Here's why I probably would have done it that way. Just glancing down, notice they tell us the region R is a base of a solid for each y perpendicular to the y-axis. As soon as you see that, you know that you have to put these equations in terms of y, in terms of x equals stuff of y. And so by looking at part B, I would have realized I have to change them anyways. Let's change them at the beginning, and then this way we only have to do one integral instead of two. Right? So either way is fine. However, it might be more efficient to convert them to x equals instead of y equals. Speaking of, let's get to part B. The region R is the base of a solid. Okay, so let's redraw that region R. Looks something like this. And then we have, I should have done it in red, huh? So it looks something like that. And then we had this green part that went here. Excellent. For each y from 0 to 2, right? So my y's went from 0, using the box as my axis just to make it a little more accurate. The cross section is a rectangle whose base lies in R and whose height is 2y. So we have this rectangle that's coming across here, okay, and its height is actually 2y. So mine is not going to be super accurate, but that's okay. We're going to come across here, we're going to drop that guy down, and then we have our rectangle. There we go. Something like that. Yeah, maybe not perfect, but that's okay. we have a base. Well, the base here, I think, shouldn't be too hard to see, right? The base is just the distance between the green and the red functions. And we already know that the green function is 6 minus y. And to find the distance, we subtract. So I need to subtract off the red function, which we found was y squared. So there's the base of my rectangle. The height, they told us, is just 2y. That's kind of a weird one. It's not like double the base or anything strange. It's just 2y. That gives us enough to find the area of a rectangle, right? The area is the base. We'll rearrange that. Negative y squared minus y plus 6 times the height, which is 2y. So then if we want the volume, it's the same thing. Minus y plus 6 times 2y, but that's only 2 dimensions, base times height. We need to give it a third, and this is across the y-axis, which means that's infinitely small width of dy. There's one rectangle. We need to sum up all of the rectangles from 0 to 2, and we're done. So hopefully you can see that connection from the first problem just by already writing it in terms of y. Makes part B go a little faster. Of course, then part C rotates it around the x-axis, so you still need to have the other one to generate a solid. So this one I'm going to, I guess I could actually do this down here, right? We could call this like my xy axis, nothing bad. And then we have our this and this one down here, and then the reflection. Reflecting this, it should actually look like a parabola. Mine's not really going to look great, but that's fine. Looks over like this, and it's nice that it's around the x-axis because instead of being a washer, there's no gap in between. This will be a disk method. We have this guy right here. You can already see it's definitely not quite even, but that's okay. Kind of comes over to here. But then we have this one at the end. We have to change functions here. Yeah, kind of strange, huh? All right, well, if we wanted to find the total volume, you'll notice that one volume has a radius, I'm not going to do it down below, of top function minus 0. So the first radius is just going to be the top function, which is that, I've already forgotten, square root of x. There we go. So we know the first part going from 0 to 4 right here, right? 0 to 4 is going to be one part of the solid, and it needs to be pi times the radius. The radius is that square root of x squared dx. So if I did that, that would find all of the red disks summed up. But then we also have these green disks. In fact, this shape over here, you might even recognize that as maybe like a pyramid, something like that, right? Yeah, something like a pyramid. You could actually take some geometry formulas and go through and find that. And we can go through and do it with calculus, though. So we're going to integrate from 4, and I think we finish off at 6 over at the end. Pi times 6 minus x squared dx. And everything's dx because that infinitely small width, right, if I added it right here, so we could see that third dimension is along the x-axis, yeah, dx. Now the problem here, though, is they asked us to find the volume of the solid, which means we actually need to be able to take the antiderivative of everything here. It's not as bad as you think, though. So this one goes 0 to 4. There's a pi, so I'll factor the pi out. Square root of x squared is just x, which is very nice. And then we add on the second integral, I'll factor out pi again, 4 to 6. In order to integrate this guy, multiply everything out. So we're going to have to do a 6 minus x times itself. I'm just working this up above, 36 minus 12x plus x squared, or rewriting it x squared minus 12x plus 36 dx. Let's go ahead and start doing our antiderivative. Pi 1/2 x squared from 0 to 4. And our second one is pi 1/3 x cubed minus 6x squared plus 36x from 4 to 6. How far am I going to go here? Not very far. Pi 4 squared is 16. Half of 16 is 8. So, and then that's 0 plus pi, and then working this guy, we're going to be incredibly lazy here. We're going to do 6 cubed, which you might not even know. It's 216, but if you're not sure about it, don't forget your extra parenthesis. We're going to just plug in 6 Plug in 6 and substitute in 6. There's the first one. Minus, watch those parentheses, and then substitute in 4. 1/3 by 4 cubed minus 6 by 4 squared plus 36 by 4. Last set of parentheses, and there we go. Great. That's our answer. Now, if you wanted to simplify this, you could. It simplifies down to 32 pi over 3. This is a free response question. It's non-calculator active. Don't waste time simplifying. If you're really bored at the end and you want to try, go for it. But remember, if you simplify and you don't get that, then you lose the whole point for the answers. You might as well just stop early and do less work. All right, last problem. Lately, they've been trying to throw some kind of curveballs with volume at you. Traditionally, it's been very similar to the ones we've seen so far. It's find area, find volume one way, find volume another way. Lately, though, well, let's look at problem 3, the funnel problem. Everyone's favorite. No calculator. Inside of a funnel has a height of 10 inches. So if we look at this guy over here is 10. Okay. Has circular cross sections as shown below. I always like to give some width to my cross section. Right, there's a bit of width right here. There we go. So if you stack those discs on top of each other, it creates a funnel. At height h, the radius of the funnel is given by r equals whatever for 0 to 10. The units of h and r are in inches. Find the average value of the radius of the funnel. Okay, well, we have two ways to do this. But if we're looking for the average value of the radius, you might think, oh, average value, I know that's 1 over b minus a times the integral from a to b of r, and then this will have to match dr. And you're not wrong. However, these guys and these will also need to be in terms of r. And unfortunately, we don't know anything else about r. So instead, let's do everything in terms of h, because I know that another way to write r is as 1/20 3 plus h squared. That is r. r is equal to that. So we'll do dh, and we know that h goes from 0 to 10. So if I work this out, this will give me the average value of r. They do actually want us to find the answer. So 1/10. I'm actually going to factor the 1/20. It's going to come hang out with that 1/10 out there. 0 to 10. 3 plus h squared. I think we'll probably have to do the same thing we did on the previous problem. In order to find this antiderivative, we'll multiply all this out. 10 and 20 are going to combine to make 200. Integral from 0 to 10. This becomes h to the 4th plus 6h squared plus 9. All right, 1/200th. I apologize for the small boxes. Normally on a free response, this would take up half the page. There's usually 4 parts to a free response, and so 2 boxes take up 1 page, 2 take up the other, but I was trying to save some paper here. Antiderivative time, we get 1/5 h to the 5th plus 3, plus 2 h cubed. 2 times 3 is 6, plus 9h from 0 to 10. And so substituting this in, we'll just use a little space down here, 1/200th times, just substitute in 10, right? 1/5, 10 to the 5th, plus 2 times 10 to the 3rd, plus 9 by 10, minus 0. Be smart about your parentheses if necessary, and we're done. I'm not simplifying that. There's no reason to, especially because it's no calculator. If you wanted to simplify, it does come out to be 109/60th, and the units are inches. They didn't ask for units, but just in case, it's there. All right, next up, tricky one. Find the volume of the funnel. This stumped a lot of my students when this came out a couple years ago, and the reason is because they looked at this and said, but wait, they didn't tell us, are we rotating this around an axis, or are these volumes by cross sections? Well, I mean, look at the problem. They told you the funnel was created by cross sections. And you can even see the cross section right here, right? These are cross sections of full circles. So what do? Well, we start with the area. Okay, so if we want the area of a single cross section, it's a full circle. How do you find the area of a circle? It's pi times the radius squared. Then we need to add a little width. What is the width along? Well, the width is along this 10 over here. Maybe think of that as an axis, right? Something like this. And 10 is height. So this little bit here is dh, which to me tells us then we need an area that only uses h. But we know h. h is 1/20th, 3 plus h squared. That's the same thing as a radius. If we want volume, volume is going to be pi times 1/20th, 3 plus h squared, squared times dh. But that's only a single disk or cross section. We need to sum up all of them. So we're going to sum all of them up from, we're along the h-axis, so from 0 to 10. Now we have some math to do. We need to actually find the volume, which means we need the antiderivative. Let's start simplifying some things down. Pi goes here, 0 to 10. The square we can distribute here and here because they're connected by multiplication. 1/20th squared, 20 times 20 is 400, and this becomes 3 plus h squared squared dh. Okay, nothing bad too far. I'm going to have the 1/400th hang out with pi out front, so I don't have to deal with that till the very end. We've already multiplied this out. This was h to the 4th, right? Plus 6h squared plus 9, right? We actually did this whole thing up above. dh. We do still need to show the antiderivative again, but this is just repeating what we've already done, so it's not terrible. 1/5 h to the 5th plus 2h cubed plus 9h from 0 to 10. And then substitute everything in. So pi over 400, 1/5, 10 to the 5th, plus 2 times 10 cubed, plus 9 times 10. Technically there's a minus 0, but we don't need to show it anymore, and we're done. I'm certainly not simplifying. If you wanted the units and the final answer, it is 2209 pi over 40, and this is volume, so it must be cubic inches. Last part. The funnel contains liquid that is draining from the bottom. It's a funnel. It does have a hole. It's probably a good thing, right? It's kind of the point of a funnel. At the instant when the height of the liquid is h equals 3 inches, the radius on the surface of the liquid is decreasing at a rate of 1/5 inches per second. At this instant, what is the rate of change with respect to time? I see a related rates question. We know how to set this up. We start with what we know. What rate is given to us? The radius of the surface of the liquid is decreasing at 1/5 inches per second. Radius, we know dr dt is decreasing at 1/5 inches per second. All right, what rate do we want to find? That's the whole point with related rates. We relate them to each other to find a rate. At this instant, what is the rate of change of the height of the liquid? So we want dh dt when what happens? When the height is 3. So when h is 3. Okay. Do we know an equation that relates r and h together? Well, I hope so. They only gave us one equation. They told us in the problem r equals, and I'll look this up to make sure I don't screw it up, 1/20th 3 plus h squared. Because we are going to do a derivative of this, I find students struggle when there's a constant on the outside. I struggle sometimes with it, so I'm going to distribute that constant in to get 3/20ths plus 1/20th h squared. All right, let's get the derivative. The derivative has to be with respect to t. All of our related rates are going to be that. So we need to go d dt of the left side and d dt of the right. The left side is just r. The right side is 3/20ths plus 1/20th h squared. So this becomes dr dt equals 3/20ths is 0. It's a constant. The 2 is going to combine with the 1/20th to make 1/10. H stays the same to the first power times the derivative of the inside. Right? We can't have a derivative that only has one rate, then the rates wouldn't be related to each other, times dh dt. All right, the last step is to evaluate the derivative with the values given to us in the problem. And so we know dr dt is negative 1/5. Okay, 1/10. We know h is 3 in this case, and we are trying to find dh dt. All right, easiest way to do it, think of this as 3/10. To get rid of the 3/10, multiply by 10/3. So negative 1/5 times 10/3 will equal dh dt, which tells us that dh dt, through some clever cross-reducing, is negative 2/3. Don't forget your units, but those should be pretty easy because we just say dh, the change in height, we know that's in inches. dt, we know that's in seconds. And we're set. It should also make sense that the change in height is negative, right? If you're losing liquid out of the funnel, then not only is your radius shrinking, right? Here's another little cross section, but the height is now shorter than it was before too. I think that's all they asked of us here. Yeah, so definitely a tricky question. You can see what I mean though about them asking about volume in different ways. I would also not expect to have your calculator for volume. So if you have those clever formulas programmed in, great, know how to use them. It might show up, much more likely that it'll end up here. I've also found that on the multiple choice, at least that I've looked, there is usually one volume question on the non-calculator active multiple choice, and there is also one volume question on the calculator active. So there might be a chance you can use those cool formulas later on. Take a quick second, even though there isn't a ton of room here, and jot down anything you think you might need to know for this. I'll remind you as we're doing our conclusion, though. The area between two curves, and same goes for the volume, should always be positive. If you get a negative answer, you probably just swapped the functions. You did bottom minus top or left minus right. To find the volume of a shape using cross sections, you find the area of the cross section first, pi r squared, 1/2 base times height, base times height. Try drawing the shape in the region. I'm not a good artist, but just through practice, I've gotten better at it. And then you integrate the area function times dx. To find the volume of a shape using disks, you're doing pi r squared, right? That's a full circle. The radius is the top function minus whatever the axis of revolution is. If you're revolving it around the x-axis, just 0. If you're revolving it around a line, like -1 that we did earlier, right, it's minus -1. And if you find the volume of a shape using washers, you do pi times the big radius squared minus pi minus times the little radius squared. It might help you to draw those two concentric circles, one circle inside the other like I did over here first. There are plenty of these released. Keep up the practice, and I'm excited to watch your success on the AP exam.